Welcome to Study Loop.
All right. In this question, we're going to do some calorimetry with steam being added to a copper container with some ice in it. And we're going to find the final temperature of the mixture and then how much ice, steam, and liquid water there is at the end. So what helps me with calorimetry is this graph that you see, which you have seen it possibly as temperature versus time or temperature versus heat, either one. And this graph shows, and since we're using water, I labeled the temperatures 0 degrees Celsius and 100 degrees Celsius on that y-axis. So our first slope segment shows the solid phase, the second slope segment shows the liquid phase, and then the third slope segment over here shows the gas phase. And what we're indicating here is that as we add heat, we get an increase in temperature. So we start off with a solid that's below the freezing point. We add some thermal energy and we bring it to its melting / freezing point. So this horizontal segment will be melting if we're going one way or freezing if we're going the other way. If we are adding heat, we're going to be melting it. If we're removing heat, we're going to be freezing the substance. And then once we've melted or frozen, well, once we've melted everything, then our liquid can warm up. And then we're going to reach the point where we are either boiling, so for water that's 100 degrees Celsius, or we are condensing. So that's our phase change. And likewise, melting versus freezing is also phase change. So we have to take all of our liquid water and evaporate or boil away all of it into gas, into steam, before we can then change the temperature of the gas phase. And what I like to do with calorimetry questions, I'm just going to focus on the water, the ice and the steam at the moment, is that we'll mark the fact that we are starting off with ice at 0 degrees. So it's still solid, but it's at 0 degrees. So, here's our ice. And then we have steam at 100 degrees. And so our steam is starting here. And what's going to happen in this process is the ice is going to, first of all melt. And then it's going to be able to warm up to some final temperature. I'm going to call it just T, actually not T final. While at the same time, our steam is going to condense and lose energy. And then the water that condenses out of that is likewise going to, let's actually do that in a different color. Let's choose like blue here. So our steam is going to lose energy, and then our water from that is going to lose energy. And we're going to have, like I said, that temperature T of the final mixture. Now, this question, we have to worry about the copper container as well. And the way I approached this question was to assume that we're going to assume that all the steam condenses into liquid water. And therefore gives up all of its energy into first melting the ice and then warming up the copper container and the cold water. And then we'll also have the hot water that condensed out of the steam losing some energy as well. So I broke this down into exactly that. I said, let's figure out how much steam has to condense, or like how much energy does the steam give up to melt the ice. And Then I found how much energy is left over after that to warm up the copper and the cold water. And of course, our steam will have condensed into liquid water in that process. So by breaking it down like this, I could figure out what's the final temp just from, so the temperature of the copper and cold water just from the steam condensing. And then I could look at, actually I don't want to put that here. So thinking of it this way, lets me first of all find the T from the steam condensing. And then what's the actual final temperature from the hot water cooling off and transferring its energy to the copper and cold water. So breaking it down this way seemed to make the most sense to me. Again, our graph only handles mixing the steam and the water. So how much energy do we need to melt that ice? So we can find the heat for that with the mass of the ice times the latent heat of fusion. And that gives me latent heat of fusion, or you might also think of it as the energy for melting, depending on which way you want to go with it. And that is 334 joules per gram. So that's 334 times 10 to the third joules per kilogram. And I got that it's going to take 31,730 joules to melt the ice. Okay, great. How much energy does our steam give off in condensing? So we'll take the mass of the steam times the latent heat of vaporization, 0.0350 kilograms times 2,230 times 10 to the third joules per kilogram. And I got that 78,050 joules are released by the steam. So our difference here is, of course, going to be what goes into warming up the copper and ice. So now that we know how much of the energy from the steam is needed to melt the ice, we can find that it's 46,320. It's going to be available to warm the copper and the ice. So we can, again, find what temperature do we reach from this process. I'm going to call that part 1. So we're going to have the heat added to the copper plus the heat added to the cold water, which I'm going to call CW, equals this 46,320 joules that's available after the steam has melted the ice. And we can find this with MC delta T for the copper plus MC delta T for the cold water. And the mass of the copper is, of course, 0.446 kilograms times 385 joules per kilogram. And we have a final temperature of T minus 0 degrees where we started, plus the mass of our ice, 0.0950, although it's now liquid water, multiplied by the specific heat of water, 4,184 joules per kilogram, again, times T minus 0, final temperature minus initial temperature. That's going to be equal to our 46,320. And so this gives me 171.71 times T plus 397.48 times T equals that 46,320. So 569.19 T equals 46,320. And I get a temperature that the copper and melted ice reach just from the steam condensing of 81.38 degrees Celsius. Excuse me. Okay, well, now we still have this phase 2 where we're in orange right now. So phase 2 is going to be the additional increase in temperature from the hot water cooling off, right? So we've got this second piece of the question. And so to do this, we can once again think about the heat added to the copper plus the heat to the formerly cold water. And that's going to be equal to the opposite of the heat lost by the hot water, right? Because one's a gain, one's a loss. So we need to assign a negative sign appropriately. And now this time, we'll be able to set up still MC delta T 0.446 times our 385. We're still going to call it T as the final temperature, but we're now talking about copper that's starting at 81.38 degrees Celsius. And now plus our mass of formerly ice, now cold water, 0.095 kilograms times our specific heat of water. And again, our temperature is going to be some final temperature, but this stuff is starting at 81.38 degrees Celsius. And that's going to be equal to minus the mass of our steam that's now hot water, 0.035 kilograms, times 4184, times a final temperature minus the 100 degrees where it starts. Excuse me. And so from here, we're going to get 171.71 T minus 13,973.76 plus 397.48 T minus 32,346.92. And that's going to be equal to negative 146.44 T plus 14,644. And now let's combine our like terms. So we're going to bring everything that has a T in it to the left side. And then we're going to add our 13,000 something and our 32,000 something to that right side. And that's going to give us 715.63 T equals 60,964.88. And that gives me a final temperature of the whole mixture of 85.19 degrees Celsius. You could call it 85.2. That would also work. So, if all of the steam had not condensed, I would have ended up with a temperature that was more than 100, which doesn't work. But it was a safe assumption to make. If you weren't sure how it was going to go, you could also have approached it by simply looking at, go step by step like we did with finding out, well, how much heat would be needed to bring copper to 100 degrees, how much heat would be needed to bring cold water to 100 degrees, and see if that amount is more than what the steam lets off, then you know that you're going to not make the copper and cold water make it to 100 degrees, and that your steam is going to condense to hot water and then also still give off more energy. So how much ice, liquid water, and steam? We have no ice because it all melted. We have no steam because it all condensed. And the kilograms of liquid water will be equal to the mass of the ice plus the mass of what was steam. So 0.095 kilograms plus 0.035 kilograms, and I get 0.13 kilograms of liquid water.